Thanks, everyone. What we're going to be talking about a bit today is what it means by discussing Linux as a safety element out of context. So this is a bit of an overview as to some of the lessons learned. And I'm going to sort of start off by talking a bit about what actually is happening with Linux these days, so you understand the scope of the problem a little bit better, and then passing it off to Nicole to talk about the safety element out of context, and then Chuck will take us home with some of the information he's got. So, first step, Linux is 34 years old. It is an established code base. It has got a lot of history behind it, and it is continuing to evolve at a pace where it has got still the most highest velocity of any open source project. And that isn't going away. It's also in a wide range of applications, some of which have federally regulated constraints, like stock exchanges and finance sectors, as well as safety constraints, things like being up on helicopters on Mars, which it's not certified for that yet, but they're heading in those directions. So we're seeing a wide range where Linux is actually being employed and used. As I'm saying, it pretty much dominates most of the supercomputer market these days. And probably the lowest sector is sitting here as embedded Linux at about 70%. This is estimates that the Linux Foundation has made over the years trying to understand the scope of Linux in the ecosystem, okay? And it's sitting on Android, it's sitting in smartphones. And mostly Linux is dominating most markets, except for the ones with the safety constraints, but we're seeing more and more pressure for it to be used in places where there is safety now. And this is why we're looking at how do we actually be able to use it effectively. Now, I just finished telling you the project velocity. This is looking from the start of the year, annually, looking at how much Linux is actually, over a one-year period, how many people are actually contributing to Linux. And you can see there's almost 5,000 developers last year that contributed, 4,700 that contributed to Linux. And that's unique individuals, okay? And you're looking at, a wide range of PRs and issues. Basically, we're looking at about 9 changes per hour going into the upstream kernel. Okay? Now, most of this is in drivers, to be fair, and the common pieces are not, the parts of the kernel itself don't change that much anymore, and it's, fairly serious, but you can sort of get a feel for the scope of the problem we've got here, which is figuring out how do we come up with a methodology where we can work with Linux and actually go after safety. These are the stats that were from that period I'm showing you at the start of the year, and we see over 2,000 contributors from 210 organizations for this one kernel, 613, okay? And this is where that 9 changes per hour. In this case, for that release, it was 8.6. It seems to vary between 8.5 to 9.2. And it's been this way about for 5 years, which is when I've been measuring it, and others have been measuring it. So we have this very rapid rate of change, and that's part of the reason people are working with Linux. Now, most of the change is happening in drivers and in other remote parts of it. But this is a factor when we're trying to work with Linux and safety. Now, as we start to look at the safety standards, they were created to address the need to minimize and mitigate systemic faults. So Linux was not designed for that type of environment, but all components of a system need to be known, tested, and managed. And if a system is using Linux, how can we do this effectively and efficiently is our big challenge. Now, in order for us to really look at starting to do this at scale, we're going to need to have our safety use cases automated at the end of the day. So we'll talk a little bit more about that. And most of what the safety cases are going to be looking for, when you actually survey them, I don't have access. The only one I have access to is one of my projects bought me. But I was working with Pete Brink, who does have access to all of these from UL, and we surveyed them. And they have certain things that they are expecting to know. And a lot of that stuff is in basic transparency for SBOMs, okay? And so getting it so we can reproduce things exactly, rebuild things exactly, is sort of table stakes here. And when you start looking at a system with safe usage considerations, the standards have been written with the view in mind that you have various needs and there's requirements on each component that satisfy them, and you can prove it all out. And this is what's been in place now for 40 plus years, okay? So longer than Linux by a good margin, but what we have a challenge is we have Linux, a configuration of Linux in one place, we have a configuration of Linux in the other place. How can we make sure that the right level of argumentation and analysis happens so that we can trust things? And this has been the big challenge. And to be fair, it is more than just Linux that we have to start thinking of these days. Obviously, hardware is now a factor here. We all know of security vulnerabilities where it's the interaction between the hardware and the software that has to do it, and certainly the safety cases when the hardware has flaws and hazards. We're going to need to make sure we can mitigate. Software, we're seeing AI showing up here, okay? This is going to be coming in that we need to be tracked as well as how it works on that, and training data sets are now part of our requirement. So the factors for doing the analysis for determinism are shifting radically, and we need to figure out how we can tackle this in a systemic way so we can eventually automate it. So this is the big question, and this is what we've been working on in the ELISA project now for a couple of years, and we've been working on it bit by bit, but one of the things we're looking at for our approaches is how do we look at Linux as a safety element out of context, and with that I'll turn it over to Nicole.
Yep. So hi, so from my side, I'll start a little bit with the theory and the explanations around it. So I'm the explanation figure like in German Kids TV today. So the safety we're talking about here, it always means in our scope that we have a freedom from unacceptable risk, whatever that means. In the sense of we don't want to injure somebody, we don't want to damage the environment, we don't want to have maybe economic damage in the end, and the functional safety part of that is that we expect a system or equipment or whatever to operate correctly, to operate it in a way that we want it to operate, and also to operate in a defined way in the case of an unexpected event, of an error, of an input that was not expected. So to have this defined and analyzed before and implemented that way. Also means that we want to have means in place to detect these dangerous situations, to prevent them, to mitigate them, to have a whatever safe state in the end in case of error or unexpected behavior. So, and what is this strange safety element out of context here? So I don't like the word safety element out of context. For me, it's a safety element with assumed context. So it has some idea, or the people creating it have some idea or some theory in mind. But yes, it comes without a real system context. So if you think about how can an RTOS harm you, it can't. The safety always needs to be determined then on system level. It needs to be determined if your car braking ECU performs as expected, if your car brakes or if it accelerates if you want to brake. It means is your washing machine causing a fire in your basement, or isn't it in the case of something breaks? So these are the things that you as a system developer care about. But as a safety element out of context, you just can assume that this will be your final destination, and you can assume what this final system destination wants from you. But yeah, you have to assume it and you have to document it, because whoever uses your component wants to validate that this really is how it is behaving. What didn't speak? Yeah. So most important thing, whatever system safety element out of context you use on your system level, and this is a point I really want to bring home today, is you as a system developer are responsible in the end that the thing that you use, the safety element that you use, performs the way you expect it to be in your system, because the element itself is completely unaware where it ends up in the end. Most important thing, even before you start real work, is to make sure that you have the compatibility, that your safety element, for example, is behaving like you, comes with the properties that you need. For example, if we use Linux as a safety RTOS or any other open source RTOS on the market, we need to make sure anyway that the compatibility is there. So for example, if you think about using it in an automotive ECU, in the end, you need to fulfill your vehicle safety goals and maybe timing constraints, that everything happens in time. If you look down to the embedded level, you want to have it compatible with your hardware, with your HAL, but also with your system level stuff on your application layer. So there is a lot of stuff that you need to think before you even start bringing things together, bringing things, for example, in a vehicle and going out on the road and then realizing, ooh, half of the stuff I need isn't there. So what do you need to expect? So it needs to behave as expected. So you need to know what you expect. It's just been created assuming a context. So you can't just expect it to be suitable for you, check it. But you have to expect, and you need to ask before you do anything, if there is sufficient documentation that also helps you to integrate it, that there is a safety manual, that there's an integration manual, that you get the assumptions of use, all that. And check that it's not only marketing, so that there is really a system or a safety element that comes with a stable architecture that you want to use, that you trust, that there is really the evidence that whatever it claims to be, it really is, so that there is systematic capability, that there has been a process, that somebody maybe independently checked if things really work as intended, that there is test coverage. Maybe talk to people, look at the evidences, really just don't believe some 2 or 3 marketing slides about that. So my most important point here is the myth busting, because there are a lot of people there, seasoned safety experts, that still think they buy a safety element out of context that has been certified, maybe for several standards by whatever agency, and that comes with a really hefty price tag, and they just integrate it and they don't need to do anything before. As I said, no. Absolutely not true. It's designed for reuse. It comes with the documentation for reuse. It comes usually with some kind of configurability. But you need to make sure that this is really what you want in your context, and you need to make sure once you have integrated it that it works as you thought it will work. Another one is, hey, it's safety certified, so I can completely forget about everything or anything concerning this element. Nope. As before, it's based on assumed conditions. It might have never been analyzed the same way you would analyze it if it would have been developed by you in your company. So check what's there. There usually you will get failure modes, you will get the assumptions, you will get behavior, defined behavior at interfaces. Use this in your own safety analysis. And if you're not happy with the depth of it, ask whoever gave you the safety element out of context for the information. If this company can't provide you with the information, or this project can't, get something else. Don't believe just that there's a certificate that you're not allowed to ask questions or look deeper. So one thing I'm getting asked a lot, so, it's certified, so I have no responsibility whatsoever. So whatever goes wrong, it's not my fault, it's the fault of the supplier. Nope. In the end, the supplier provides you with the documentation and provides you with all you need for integration, but yeah, you're the one who has to rate in the end if this is good enough for you. So, very similar to the one before. it's certified, so I don't need to understand what it's doing at all because it's plug and play. And yeah, I don't need to include it in my analysis. I don't need to do anything. Nope. You need to understand at least roughly how it behaves in your context. Once again, there must be information available for you. If the information you need is not there, ask for it, or if you don't get it, forget about it, because you're responsible. You can't then just finger point and say, hey, I bought this here and there. Nope, it does not work. And there are people saying, oh, it's not applicable to software. We always need a hardware, or we can only do this with hardware. Nope. You can assume a context on anything that you can define interfaces for, that you can integrate somewhere. So you can do this for an RTOS or for an interface library, for a communication stack, for whatever. You can, define a defined scope. So yeah, it's certified. I use it and my system is safe. No, there is no safety plug and play. There never will be. And safety is a system property, and make sure that things work in your context and not just on their own. So there are some responsibilities to the integrator. So yeah, it's not plug and play. I know I repeat myself, but this is from my side, from the theory side, the most important thing. It's not plug and play. Don't expect a certified component to be your solution to your crappy product. And even before you start, review the safety manual. Ask for the safety manual before you start. Ask for the safety manual before you commit to something. Make sure that the limitations and everything works for you. Maybe you would need to have so many input-output checks implemented on your side that you would say, oh, I can do it myself, check faster than integrating that. So make sure it works for you, what's assumed and what's the obligations that come with it. Assess if, the functional and technical compatibility is there. Evaluate if the certification scope even works for you. You know, sometimes it's certified, and then I say, well, for what? An automotive ISO 26262 certification might be great for an automotive ECU, but if you want to bring that into a heavy machinery running 24/7 without being stopped, this certificate won't work for you. Just look at especially if it's about hardware, look at the uptime of the systems that are in relation to the safety analysis there, and you will see not every safety certificate can be used for each domain. And know what you want to have, know what to expect. Be sure what you want to buy, what you want to integrate before you look for it. Just don't say, oh, we need an RTOS and we want a certified one. You want an RTOS and you want it to have certain things it brings with it. That's the important thing, not that it has a certificate. It needs to work functionally for you. And then the next goodie is if it has a certificate or if it has qualification evidence that you can reuse for your stuff. During engineering, just don't do it blindly. Validate that what you thought about it works. Check it with your test cases, that it works as intended with your functionality, that you have the response times that you expect, that the interfaces work as expect. Include it in your own safety analysis. It's not a blob. You need to make sure that you know how it behaves and where you need to catch some error conditions. Apply the configuration and parameterization that is usually then described by the safety manual. If there is nothing, ask for it. If they can't answer you, don't go for it. And trace requirements. Make sure that you really have the traceability between your needs and the requirements and safety claims that come with the component. And run your integration tests with it. Don't wait till the end. Run it, test and fail as early as possible. Perform your safety validation with it in it, and include it in your safety case. Just don't say, hey, we have a certified something. Include it, we have a certified something in this version with this documentation, and we are sure that this is exactly what we needed because of your traceability. And perform the safety assessment, including everything, either with your internal QM with somebody from external, whatever is needed for you. So my advice with, I don't know, 20 years of working with this and being frustrated till the end, always look into the safety manual. Don't buy it because of 2 or 3 marketing slides. Look into the safety manual, look into the assumptions, look into the obligations, and check if this works for you. And to decide on a safety element out of context to be used, it's a starting point. It's not the complete safety solution. You're responsible for the solution. So it's a starting point. It will help you for sure because you don't need to do some things, but you still need to do a lot of things. So, and then over to Chuck.
Excellent, thank you. Okay, so I'm going to talk to you about using the Linux kernel as a safety element out of context. Just for more context, this is not economically feasible to do in a proprietary environment. So it's open, and that means it's audacious, what we're proposing here. So I get that. The engineering discipline we're talking about here with all of this safety stuff is called design assurance. It goes way back, and it's made up of 3 legs: hazard identification, and if it's a security thing, it's threat identification, or if it's just you're building a calculator, it's just use cases. So any of those things apply. And then design mitigation, and then implementation assurance. So hazard identification in this case for safety is what could possibly go wrong, right? Identify this. Then with design mitigation, you have to actually show that the safety measure or safety requirement is baked into the whole design. You're not going to watch your new model car come off the line and someone says, you know, I really don't want the wheels to skid when I lock up the brakes. Let's do anti-lock brakes. Well, that's just going to be a hack at that point. It's bolted on, right? So if you look at anti-lock brakes, the system, it's baked in all the way from the electrical, mechanical, everywhere. It's just a huge, huge impact to the system. So that's why it has to be baked in at a very high level. We'll talk about a little more about that here. And then, of course, implementation assurance. Does your implementation, does the thing produced match the design? Doesn't matter if you have a good design. Prove to me that the actual build matches the design. So it's these 3 legs that create your design assurance, which is writ large in every safety certification document, ISO, DO, all of those. If you squint hard enough, you hold it back far enough, it's all design assurance inside of those. That's really what it boils down to. So hazard identification is the only one that we don't do, right? That's up to the OEM, ARP, there's an ARP standard for that, for aerospace. There's people who, like, that is their job, nothing else but to think of the horrible things that can happen with a vehicle. And then those are the ones who cast down from on high safety or security or whatever requirements to hapless engineers like me or Nicole or anybody trying to do these things, and then we have to implement them in. So let's look at design mitigation. So I don't know about you, but it came as a surprise to me when I got shot out of college. Someone asked me, what is the purest form of design? How do you show your design? I would have obviously said, clearly it's a picture, it's a graph. That's actually not true. It's actually requirement-based design is actually what gets you to driving out nuance. So at the highest level, we call them like tier 1 requirements. That's the big idea. That's where your board of directors says, I want 4 seats, 0 to 60 in 2.3, or it's a hunk of metal carrying 500 people, 650 miles, but whatever, kilometers per hour. That's the big idea. Tier 2, right around in there, that's where you're going to get your hazard assessment requirements, your security requirements. So I colored that just to give you an idea how this looks. I colored them. So these are the tier. These decompose down. So when you say I want this car to go fast, then the safety people are going to rain on your parade and say, yeah, but I don't want to kill people. So you got all these safety requirements. That's going to happen in tier 2. You descend down in there, and you can see how the requirements sort of blend down. It's obviously, and none of this is to scale, of course, but the requirements kind of blend down, and you'll see as you get to the bottom, you really can't tell where the safety and security originally appeared and how they affect. That's why it's kind of a misnomer when someone says at the very bottom, well, is that a safety or security requirement? I have no clue. I have no idea. It's like it's all it's all colored in like blended color by the time you get to the bottom. If you want to know if it's truly a safety, whatever, that you got to go up higher. So when we talk about safety element out of context, we're in general, not always, but in general, looking at sort of a subset of the lowest set of requirements. And then your OEM is gonna have, you know, their breakdown. And a subset of these requirements might be like the Linux kernel in here. They'll trace, so there'll be a job, like Nicole was saying, you have to then go from your big idea down and then trace into the safety elements. So these are artifacts you're going to be delivering. Either you're going to go buy it from Wind River or you're going to go open source, whatever, but you got to be able to trace down from your OEM level desires into attach points, requirement level attach points. And then, of course, at the very bottom, you have your implementation. The lowest type of requirements, we might be calling tier 5. There is no sane reason why you would want to have any more detail than code. So tier 5 requirement should be something where I can write it down on a piece of paper, lock you in a room, and that is all you need to implement the code. You don't need any more detail. That's kind of how it's characterized. So that's design mitigation. I can mitigate the design, the issue all the way down into the lowest level requirements. Implementation assurance, this is verification, not validation. Validation is, did I make the customer happy? Did it do what they want? Verification is, did I do what I intended here? So implementation assurance says, did I do what I intended? So from a requirement, from a shall statement, you can write a test case. Is the kernel being tested today? Are there tests written for the Linux kernel? Yes, shake your head. Are any of those based on reality? No. No kernel maintainer has sat there and said, yes, that is a completely 100% accurate idea of what the code is supposed to do. It's an educated guess. We're all very intelligent people, but you cannot show me full coverage of all those test cases we've written for the kernel. The maintainer has signed off on the test, saying that is an accurate reflection of what the code says. So we actually have a logical gap right now, today, between those. But if you have a written requirement from which the code is expected to be derived, you can write a test that should accurately reflect that. Now, if you have a kernel maintainer who has signed off on that requirement, saying that is an accurate view of the implementation of the code, you write the test. Now you have code coverage proving that you covered, your test actually hit all the code that you want to. You have this virtuous cycle. It'll verify what it was intended. It may not be valid, okay? It may not do what the developer expected, but at least you know the implementation matches, or we got to fix a test case. You can shore these things up and create a very tight loop here after a while. That's implementation assurance. Now, safety is not a monolith, okay? I have not done a formal study. I imagine maybe someone has. I am reasonably certain, just having been in the industry for 23 years, commercial aerospace is actually the most rigorous level of engineering. We have managed to find the most complicated way to verify things, and that is because what we call risk acceptance, okay? Astronauts sign on the dotted line. They know that there is a greater, very high likelihood they will not come home alive, all right? I mean, if you add it up, if we had the same death rate among astronauts in commercial aerospace, we would not have a commercial aerospace industry. So we're looking at 10 to the minus 10th, 10 to the minus 11th, 12, like never happen in an entire universe level of reliability in commercial aerospace. Engineering rigor obviously has to go up dramatically with risk. When risk acceptance is very, very low, engineering rigor has to go up, which means the amount of complexity that's feasible goes down, and of course costs skyrockets. Compare that to your YOLO coding, right? You accept a ton of risk, very little engineering rigor. You can put all the complexity you want in there, and cost is whatever you want to make it, okay? This is obviously not to scale. Even in commercial aerospace, there are different levels, okay, of rigor. The point is, though, if we're doing something in the open source community to say, let's do this once, let's do it right, let's onboard onto projects, not saying, hey, make us safety people happy, because that's never going to happen. We have to buy our way on to the airplane, if you will, with quality. We have to tell maintainers that we are going to make your life measurably easier because we're going to shore up we're actually going to reverse engineer, we're going to shore up the design, all these things. There has to be a payoff here. So what's the superset? What do we want to shoot for? What do we want to shoot for so that we can make all the industries happy? Probably happens to be DO 178. There's 5 hazard levels. We're shooting for the catastrophic hazard level, okay? There are 71 objectives, 30 of which have to be done with independence. So let's figure out how close what we're doing and how close we can get to success here. So we've got a safety profile we're working on. This is the whole certification process. This is building your documentation, tracing your requirements, tracing your test cases, tracing your verification results, tracing all those things. We're extending the software package data exchange format for functional safety. So Nicole is leading that, doing an excellent job. Getting ready to release our first iteration, I think with SPDX 3.1. Thank you very much. Our first iteration, 3.1. We have a long way to go, but we've made a lot of progress. Okay. Back of the napkin, I think we could squint and say that's probably going to nail about 22 objectives. Okay, for DO 178. Now that doesn't mean the work is free, but it means now you've kind of got some guardrails to work within that. So, okay. And by the way, if you want to get involved, we'll talk about call to action here at the end. Linux kernel requirements, that's the big one. When you go from functional safety, which is level D and E in aerospace, okay, to design assurance, design assured, you have to cover all the lines of code with code coverage, which means you need requirements dictating every single line of code, every function, everything that you're running in your system. So Gabrielle is running the Alyssa Safety Architecture Working Group, and this is where we're working on low-level requirements for the Linux kernel. This is templating them so we can tell when a requirement is out of date and needs to be updated. This is doing all the work with the kernel maintainers to figure out the right format and get this socially acceptable, get the wording right. Boeing is involved in this. I believe this is probably about 21 DO 178 DALE objectives covered, okay? And then code coverage. Now there are 3 different types of code coverage that need to be used when you are creating certification artifacts. There's of course statement, there's decision coverage, you would probably think of it as branch coverage, and then there's MCDC coverage. I can talk more about those. I don't want to take a lot of time to talk about all the different types of coverage. I'm fascinated with them, but that's for another talk. So Boeing had Steve Vanderleest, technical fellow at Boeing, led a collaboration with University of Illinois Urbana-Champaign to figure out how to do Linux kernel code coverage. There are a set of patches now in play to use LLVM to do code coverage of the Linux kernel. We've got results. We're still working on those code patches. We presented at Linux Plumbers Conference last year. And then we're working, this collaboration has now moved on to what's called object code coverage. So in DO 178C for DALE, you not only have to prove that your lines of code are covered, but when you produce the binary object file, you actually have to map all of the things that are running there to actual code to make sure that the compiler didn't put things into your object file. That work is ongoing. So we figure that's about, I think, about 10 DO 178C DALE objectives covered. Where does that leave us? So we got to do a lot of testing. So that's the next thing after kernel requirements. We got to work on kernel testing. That's going to be about 21 DO 178C objectives. And then there's miscellaneous OEM level responsibility, attending your audits, talking to the FAA or whatever your regulators are. There's about 10 of those. So ultimately, this gets us pretty close, and it also adds a phenomenal amount of reliability to open source software. So everybody wins. Let's talk about a call to action. Through the Alyssa Aerospace Working Group, Boeing is, we got a Boeing engineer, Matt Weber, leading that, where they're working on a minimal Linux kernel. Less code means it's easier to write requirements and run tests. Functional safety profile, SPDX. Okay, Nicole Pappler is running that. Reverse engineering the Linux kernel. Gabrielle Paolini is running that as part of the Alyssa Safety Architecture Working Group. Email me if you want to talk about Linux kernel code coverage. There's still some work to do there. And of course, there's the testing okay? Creating the test profile and specifications once we have kernel requirements. We need your help. This is your call to action. If you want to get involved in this, this is not just for safety. This is about reliability across the board. I think this is going to attract a lot of attention. Any questions? Thank you. Answer questions. There you go.
Does anyone have any questions? Like I say, we threw a lot at you here. So- Okay, Nicholas.
So how do you treat non-determinism of the Linux kernel as testing?
Like with random number generators or things like
We need to repeat the
So
question.
the question was, how do we treat non-determinism with the Linux kernel?
So paths are not deterministic.
So paths are not deterministic, right, with the code, with the coverage.
An example of that would be, like, do you want to give an example?
Yeah, you execute read, and read once just goes the shortest path through. The second time it's interrupted by an RCU call, branches out into RTU, or it branches out to the KMM cache refill. Yeah, there's myriads of paths that are possible on a read.
Yeah, exactly. And it's not only that, but the kernel is incredibly polymorphic. So now you add, so what you were talking about is there's all sorts of paths through the kernel just for a read, right? And then you throw in different architectures on top of that, and they have their own way. So if you're using it as a safety element out of context, you're going to have to minimize the things you do in there. So when we write a requirement at the Linux kernel level, at the open source level, we're going to have to start somewhere and write a test for it. If the test comes out successful, that's okay. But when you use it as a safety element out of context, you're going to have to decide what pieces of the kernel you're going to remove to shore up where your code paths, where the execution path occurs.
And this is part of the reason why we're going to need to make sure we have some minimum configurations. We've done the analysis on properly, and that's part of why the minimum kernel that
Minimal
Boeing-
kernel.
the minimum
Yeah.
kernel that we're looking at with aerospace is a starting.
An absolute minimum linking cursor.
I-
The Linux kernel execution paths
Yeah.
are not deterministic. A read
Yep.
system call on the minimum configuration has hundreds of possible paths.
Correct. And so there's various testing we're going to be having to work with to basically try to make sure it's otherwise
So
the
you want
statistical
to
side.
achieve complete coverage, but you actually don't know the possible path.
Well, that has to do with your functional use case. So if you're saying read for a specific use case, or you're reading a serial interface, something like that,
I'm talking about you do a read dev null
right?
in a tight loop
Mhm.
10,000 times, you will have 200, 300 different paths that were executed.
Right. This is not, and that's why I said, I started out saying, this is an audacious path we're heading down here. You're pointing out one of the big problems we're going to have to tackle. I don't have answers for everything you're asking.
Can I chime in?
Good, yeah.
So basically, what we are doing, so within ELISA, so we have developed a tool that is called KeySnuff to evaluate the theoretical call tree that can be reached from a given function call for a specific compiled binary image of the kernel. So that is a tool that can be used, to evaluate the theoretical call tree. And then, as Chuck was saying, we need to evaluate what is the specific use case that would effectively, justify why certain paths can be taken and why others cannot. So, but basically what we are doing is, so right now we are starting from certain functions, and we are, starting writing requirements and possibly tests for these functions, and then we'll go and continue for the dependencies. So, I mean, we cannot solve, the whole problem at once, right? So we need to decide, where to start and where to focus first.
Also, let me add one other thing. Determinism does not mean deterministic code paths. Determinism is deterministic outcome. So it doesn't matter if, let's just say I have some range of timing I'm allowed for whatever my catastrophic use case is.
Whatever your system is.
Whatever it
asking for.
is, it doesn't matter if it took 75 different routes through it, as long as the outcome is as expected, as long as it passes the required expectations. That's really what you're shooting for in a safety context.
You're ignoring freedom from interference. You're just
Yes.
Doesn't cover freedom from interference.
That's still another requirement. If you say, I need to have interference, freedom from interference from this, that is another testable requirement. And that's going to happen at a higher level. So these are all the things that have to be specified. Whenever you find an interaction that is adverse, that becomes a set of requirements that has to become testable and descends down into implementation detail.
Yeah, sorry, I've missed the first few minutes of the presentation because I was at another talk. So maybe the answer is obvious. But you said for DO178C DAL A, there are 71 objectives, and you have a plan for covering 31 of them, right?
More than that.
Way more than that, yeah.
Yeah. I think
Yeah.
we're getting
Like
close.
all but, I think we're,
Doing all but 21.
yeah, like, yeah, and we could argue
21
about these.
plus 10, 21 plus
We
10.
could slice hairs on these all day long, but yeah, like probably 10, I think is, if you squint, I think 10, I don't think we can do in open source. And that's like audits with
Yeah.
your auditors and stuff like that.
My question is, isn't DO178C DAL A too ambitious as a first? So
I don't understand that word.
no, no.
Why
No,
would I
mean-
be here? I'm not interested I'm not interested in easy. I'm here for a challenge.
Okay.
I understand
Okay.
it's almost bordering on insane and you may question my sanity, but I want to climb a mountain. Everest is too busy. There's too many people on it. So I'm looking for an interesting challenge. This is an interesting challenge.
Okay. So maybe the question becomes maybe to Kate: are you aware of attempts of qualifying Linux as safety element out of context, say for IEC?
Yes,
Yes.
I've seen up to C.
Okay.
And I've also seen people who've done it, who've taken 8 years to do it. Okay, and they're not public about it. But they basically, when they talk to me, they've taken a large amount of time. The thing that's good as a byproduct of this work is we are finding bugs and we are flushing them out of the kernel. And so as we get more and more requirements put into play, and the testing linked to the requirements, we can become much more efficient with testing the kernel, which is missing right now. We're working with the kernel CI folk to start hooking tests to requirements as well. So, but part of the dividing the requirements, we're finding bugs, we're fixing bugs, we're making it visible. And if people want to migrate from C language to another language in future, we also have a way of saying you're done. Okay, and that's not missing today. So if we want the kernel to be a sustainable artifact for the next 50 years, putting this level of system engineering in place is going to give us a better foundation than we have today. And that's most of the game.
That's the takeaway, is testing right now is only an educated guess. No one can tell you that a maintainer signed off on those tests. It doesn't happen.
Okay, any more questions? Or, oops, yep.
So
Go
I don't know if it's a controversial question,
Sure.
but kind of how high is your Mount Everest? So how much effort do you expect it would take? How many, engineering months?
That's a
And-
really good question. So I clearly am not going to do all the work myself, right? But there is, once we have set this pattern in place, and once we've got testing, once we show that a developer, a maintainer has signed off on the requirement, we've got a test case, we've got this loop that ties it all together, I believe the Googles and the Facebooks and the Microsoft, everybody who uses the Linux kernel is going to realize, oh, they have found a path to verification, not validation, don't confuse the two, verification, true verification from idea to implementation, tying those very tightly. I think we're going to get a lot of people go, oh, they have found the path, let's start following. So I'm hoping to be a leader here also. Be my Sherpa.
The other side of it too is, definition of success from my perspective is if we start getting people contributing analysis the same way they contribute code upstream, then we can scale. Okay, it's never going to be one company able to do it. They'll be able to do it for their one little case, etc. But if we can get to the stage where we can all collaborate on the analysis, get the maintainers to review it, build up the confidence, I think it will put the Linux kernel in a very good position.
That's the other part is requirement writers, and they are not the same thing as coders. We're creating separate paths of maintainership expertise here.
Well, I think we're sort of at time. So
Thank you.
Thank you very much for your attention and the good questions.